Hello students, in today's lecture we'll discuss about chemical bonding and molecular structure which is given in unit 4 of class 11 chemistry according to NCERT syllabus rationalized for the year 2023-24. Scientists are constantly discovering new compounds, orderly arranging the facts about them, trying to explain with the existing knowledge, organizing to modify the earlier views, or evolve theories for explaining the newly observed facts. As you know, matter is made up of one or different types of elements. Under normal conditions, no other element exists as an independent atom in nature except noble gases. However, a group of atoms is found to exist together as one species having characteristics or properties. Such a group of atoms is called molecule. The attractive force, which holds various constituents like atoms, ions, etc., together in different chemical species, is called a chemical bond. After studying this unit, you will be able to understand KÖssel-Lewis approach to chemical bonding. Some of these theories and concepts are KÖssel-Lewis approach, valence shell, electron pair repulsion theory, valence bond theory, and molecular orbital theory. This is a very interesting topic and important for understanding the chemical bonding and molecular structures. Please listen to my lecture carefully and note down all the important points. I welcome you once again. KÖssel-Lewis approach to chemical bonding. In order to explain the formation of chemical bond in terms of electrons, a number of attempts were made, but it was only in 1916 when KÖssel and Lewis succeeded independently in giving a satisfactory explanation. They were the first to provide some logical explanation of valence, which was based on the inertness of noble gases. So, the electrons in the outermost shell take part in the bond formation and determine the combining capacity of valency of atom. The outermost shell of any atom is called its valence shell, and electrons present in the valence shell are called the valence electrons. We have studied about valency, valence electrons, and etc. in our previous video. Hence, the electrons in the outermost shell take part in the bond formation and determine the combining capacity or valency of atom. The outermost shell of any atom is called a valence shell, and the electrons present in valence shell are called valence electrons. When two atoms of same or different elements approach each other, the energy of combination of atoms becomes less than the sum of the energies of two separate atoms. Please note, the energy of the combination becomes less than the sum of the energies of the two separate atoms at a large distance. We say that two atoms have combined or a bond is formed between the two. The bond is called chemical bond. The combination of atoms leads to the formation of a molecule that has distinct properties different from that of constituent atoms. The stable electronic configuration of noble gases can be achieved in a number of ways, either by losing or gaining or sharing of electrons. Accordingly, there are different types of chemical bonds like ionic or electrovalent bond, covalent bond, coordinate covalent bond. In addition to this, we have a special kind of bond called hydrogen bond. We will study about the hydrogen bond in the next video. In this session, we will describe ionic or electronic bond, covalent bond, and coordinate covalent bond. KÖssel, in relation to the chemical bonding, drew attention to the following facts. 1. In a periodic table, the highly electronegative halogens and highly electropositive alkali metals are separated by noble gases. The formation of a negative ion from a halogen atom and positive ion from an alkali metal atom is associated with the gain or loss of an electron by respective atoms. The negative and positive ions thus formed attain stable noble gas electronic configurations. The noble gases, with the exception of helium, which has a duplet of electronics, have a particularly stable outer shell configuration of 8, that is octet electrons. The negative and positive ions are stabilized by electrostatic attractions. Chemical bonding. According to KÖssel's theory, in the process of formation of ionic bond, the atoms acquire the noble gas electronic configuration by gain or loss of electrons. For example, NaCl. The formation of NaCl from sodium and chlorine according to the above scheme can be explained as Na, that is sodium, whose electronic configuration is 2, 8 and 1, oxidizes to become Na plus 2, 8 and plus 1 electron. That is, it becomes 2 and 8. That is, the formation of Na is by the losing 1 electron, and hence 281 configuration becomes 28, and change in enthalpy is delta H is equal to 493.8 kilojoules per mole. Similarly, the electronic configuration of sodium ion, that is the atomic number is 11, is 281. Since it is highly electropositive, it readily loses an electron to become to stable configuration of nearest noble gas, that is neon atom. It becomes a positively charged sodium cations, that is Na plus, in the process. On the other hand, the chlorine atom, whose electronic configuration is 2, 8 and 7, requires 1 electron to acquire stable electronic arrangement of an argon atom. It becomes negatively charged chloride anion in the process. So please note, the chlorine atom has an electronic configuration of 287, and to complete the outermost shell in octet, it requires one electron to acquire the stable electronic arrangement of an argon atom. It becomes a negatively charged chlor- chloride anion in the process. Hence, the equation can be written as chlorine accepts one electron and becomes Cl minus. Hence, the electronic configuration is written as 287. It accepts one electron and the total electrons after combination is 288. And the change in enthalpy delta H due to this combination is delta H is equal to 379.5 kilojoules per mole. We have studied about this change in enthalpy in our earlier chapters. These two reactions, that is formation of NaCl in terms of KÖssel's theory, that is NaNCl, is also shown on the insert box on the screen. So Na, as expressed earlier, has electronic configuration 281 and chlorine has 287. So chlorine accepts one electron whose chlorine's electronic configuration is 287. It accepts electron to form Na plus, which is 2, 8 plus chlorine, which is negative 2, 8 and 8. According to KÖssel's theory, there is transfer of one electron from sodium atom to chlorine atom as shown above, and both atoms attain noble gas configuration, that is neon and argon. The positively charged sodium ion and the negatively charged chlorine ion are held together by electrostatic attractions. The bond so formed is called electrovalent bond. Electrovalent bond are an ionic bond. Thus, the ionic bond can be visualized as the electrostatic force of attraction that holds the cations and anion together. The compounds so formed are termed the ionic or electrovalent compounds. Octet rule. KÖssel and Lewis in the year 1916 developed an important theory of chemical combination between atoms, which is known as electronic theory of chemical bonding. According to this theory, atoms can combine either by transfer of valence electrons from one atom to another, that is gaining either by gaining an electron or losing an electron, or by sharing of valence electrons in order to have an octet in their valence shell. This is known as octet rule. The Lewis-Langmuir theory can be understood by considering the formation of chlorine molecule, which we'll discuss in the next slide. Covalent bonds. We have just studied about KÖssel's theory of chemical bonding, according to which atoms can combine either by transfer of valence electrons from one atom to another, either by gaining or losing or by sharing of valence electrons. Like KÖssel, Lewis also assumed that atoms attain noble gas electronic configuration in the process of bond formation. However, the way in which the noble gas electronic configuration formation is somewhat different. Lewis proposed that this is achieved by sharing of pairs of electrons, not by gaining or losing electrons. It is, according to Lewis theory, it is sharing of pairs of electrons. Both the atoms contribute an electron each to this pair. For example, consider two hydrogen atoms to form a molecule by sharing a pair of electrons. This process is shown on the inside box. So, two molecules of hydrogen where electrons are shown by dots. These dots represent the electron of hydrogen atom. Two atoms of hydrogen combine to form a molecule. This is a molecule by sharing a pair of electrons. So here it is pair of electrons. If the electrons are indicated as dots, formation of hydrogen molecule can be shown as H double dot H or H dash H as shown in the insert box on the screen. This shared pair of electrons contributes towards stability of both the atoms of hydrogen and is said to be responsible for bonding between two atoms. Such a bond is called covalent bond. This bond is called covalent bond, and compounds so obtained are called covalent compounds. Langmuir in the year 1919 redefined the Lewis postulations by abandoning the idea of stationary cubical arrangement of octet and by introducing the term covalent bond. The Lewis-Langmuir theory can be understood by considering the formation of chlorine molecule, whose diagram is shown on the screen on the right hand side. The formation of chlorine molecule can be understood in terms of sharing the pairs of electrons between two chlorine atoms. See here there are two. This is one chlorine atom with 7 electrons in the outermost shell combined with another chlorine atom with another one. The distribution, the electronic configuration of this chlorine is 3s2 3p5. So totally you have 7 valence electrons. The formation of chlorine molecule is due to sharing of pair of electrons between the two chlorine atoms. See here the two electrons are shared here between two chlorine atoms. Each chlorine atom contributes one electron. This chlorine atom contributes one electron and the other one is contributed. So there are one pair of electrons. In the process, both the chlorine atoms, attain outermost shell octet, that is 8 octet of nearest noble gas, that is argon. So this can also be represented as dash chlorine dash Cl. Here in between this combined. This is bond. This dashed line is called bond. And we will study about this bonding and Lewis structure, Lewis dot representation in the next slide. Lewis symbol. G. N. Lewis, an American chemist, introduced simple notations to represent valence electrons in an atom. These notations are called Lewis symbols. The Lewis symbols, that is a dot representations for different elements in group 2 are shown here. For lithium This is 1 electron, barium, 2 electrons, one here and one here. Beryllium, for boron it is 3, carbon it is 4 here, 1, 2, 1, 2, 3, 4. For nitrogen it is 5, 1, 2, 4 and 5. Oxygen, freon and neon are shown on the screen. Thus, the number of valence electrons helps uh, to calculate the common or group valence of the element. Thus, the number of dots around the symbol represent the number of valence electrons. Number of dots is equal to number of valence electrons. Please see the table shown on the screen. Here, the electron dot periodic table for group 1, 2, 3, 4, 5, 6 and 7, as well as the noble gases is shown here. Here you see how it starts with hydrogen. First group, first period hydrogen, and the noble gas helium has got 2. Similarly, in the second period, lithium, beryllium, boron, carbon are shown here. In this table, this blue color is a metal and yellow color is non-metal. And this is metalloid. The other colors here greenish, slightly greenish is metalloid. Please pause this video and note down the electronic configuration or Lewis symbol notation, electron dot periodic table of each of some of the elements shown on the screen. In the formation of a molecule, only the outer shell electrons take part in chemical combination, and they are known as valence electrons. The inner shell electrons are well protected and are generally not involved in the combination process. Please note once again, the inner shell electrons are well protected and are not involved generally in the combination process. The group valence of elements is generally either equal to the number of dots. The valence is equal to the number of dots in the Lewis symbols, or 8 minus number of dots or valence electrons. Lewis representation of simple molecules, that is, it is also called as the Lewis structures. Lewis provided a very convenient way of representing bonding in the case of simple molecules. This is called Lewis electron dot structure, or simply Lewis structure. One example is chlorine. Two atoms of chlorine combine to form the chlorine molecule, which is shown on the screen in this screen, as well as we discussed it in our previous slide also. The dot representation of electrons are referred to as Lewis dot structures. The Lewis dot structures can be represented for other molecules also, and it is shown on the screen. On the screen is shown each of the CCl4, carbon tetrachloride. Each of the 4 chlorine atoms, see here CCl4, each of the chlorine atoms along with the carbon atom in the center attains an octet configuration. So here 2 Here you see two electrons from one chlorine atom, another two atom from the chlorine atom, 2 plus 2. It forms 8. So individually also it is 8 electrons in this chlorine, 8 electrons here and 8 electrons here and 8 electrons in the outermost one. Here the Lewis dot structures can be written for other molecules in which the combining atoms may be identical or different. See here in this case the combining atoms are different. The important conditions being that each bond is formed as a result of sharing of electron pair between atoms. See here each bond, here it is a one bond, is formed as a result of sharing of one electron pairs between atoms. Each combining atom contributes at least one electron to the shared pair. The combining atoms attain the outer shell noble gas configuration as a result of sharing of electrons. See here, each combining atom attains the outermost shell of noble gas, that is 8e minus 8 electrons in the outermost orbit, octet. Thus, even in the case of water and carbon tetrachloride, the carbon tetrachloride is shown on the screen, formation of covalent bonds are represented and shown in the figure. Please pause the video and note down the configuration in case of each of the four chlorine atoms along with carbon atom at the center, which attain the octet configuration, octet of electrons. Thus, when two atoms share one electron pair, they are said to be joined by a single covalent bond. So, when two electrons join, it is called single covalent bond. In many compounds, we have multiple bonds. So, here one compound is there, we can even have multiple compound between them. If the atoms share two pairs of electrons, the covalent bond between them is called double bond. See here, in case of carbon dioxide, here four electrons are combining, 1, 2 plus 2. So here there are double bonds. So it is called double bond. Thus, if two atoms share two pairs of electrons, the covalent bond between them is called double bond. For example, in the case of carbon dioxide shown on the screen, we have two double bonds between carbon and oxygen atoms. Similarly, in the case of ethane molecule, the two carbon atoms are joined by a double bond. So, this example is for C2H4. Here you see two electrons, it is having a double bond. It can be written as C as shown on the screen. Please pause the video and note down all these diagrams and practice them. Yet another example is nitrogen molecule. Nitrogen molecule is also shown here, and here there are three triple bond. This is a triple bond. That is for N2 molecule, N plus N, nitrogen atom plus nitrogen atom combine, and there are triple bonds. Lewis representation of some other molecules like hydrogen, oxygen, ozone, NF3, CO3 minus, HNO3 are also shown on the screen. Please pause and practice, note down and practice. In the case of C2H2 molecules also, it is shown here that triple bonds are shown. In order to understand the applications of chemical bonding and molecular structure, let us solve some worked examples. The first example, question number 1 is write the Lewis dot structure of CO molecule. Answer. The first step is to count the number of valence electrons of carbon and oxygen, and these are 2s2, 2p2 and 2s2, 2p4. 2s2, 2p2 is for carbon and 2s2, 2p4 is for oxygen. Hence, the total number of valence electrons available are 4 plus 6, that is equal to 10. The skeletal structure of carbon monoxide is written in the second step as CO, and the structures are shown in the diagram inside the box on your screen. So these are left side of C is 2 and around oxygen it is 8, or it can be written as 2C dash, and that is around oxygen 6. This dash is a single bond between carbon and oxygen. Hence, it is a single bond or shared electron pair between C and O and complete octet on oxygen. The remaining two electrons are the lone pair on C2. This does not complete the octet on carbon, and hence we have to write multiple bonding, in this case triple bond between C and O as shown in the diagram below. This satisfies the octet rule condition for both the atoms. Please see here, in between carbon and oxygen there is a triple bond here shown by 6 electrons. It can also be written as 2 electrons on the left of C, and between C and O there are triple bond, 3 parallel lines, and on right of oxygen is 2 electrons. This completes the answer. Next question. Question number 2. Write the Lewis structure of nitrite ion NO2 minus. Answer. First step, count the total number of valence electrons of the nitrogen atom, oxygen atom, and additional one negative charge equal to 1 electron for this negative charge. 1 electron extra. So, the electronic structure can be written as for nitrogen 2s2 2p3 and for oxygen 2s2 2p4. The total number of electrons are 5 for nitrogen, that is superscripts of S and P 2 plus 3 plus 6 of superscripts of oxygen 6 into 2 plus 1 for electron. So total 18 electrons are there. The skeletal structure of NO2 minus is written as ONO, and the single bond or shared electron pair between nitrogen and each of the oxygen atoms completing the octets on oxygen atoms. So this is drawn as shown on the insert box on the screen, and this however does not complete the octet on nitrogen if the remaining two electrons constitute lone pair on it. Therefore, we have to write multiple bonding between nitrogen and one of the oxygen atoms. In this case, a double bond. This leads to the following Lewis dot structure shown on the screen. So here it is 4 electrons around oxygen on the left and above, and in between oxygen and nitrogen one double bond, and the between nitrogen and oxygen on the right hand side it is 6 electrons and a single bond. This completes the process. Lewis dot structures in general do not represent the actual shapes of the molecules. In case of polyatomic ions, the net charge is possessed by the ion as a whole and not by a particular atom. It is, however, feasible to assign a formal charge on each atom. The formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of valence electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in Lewis structure. Hence, it can be expressed as, that is, the number of electrons assigned to that atom in Lewis structure can be expressed as formal charge on an atom in a Lewis structure equals the total number of valence electrons in the free atom. Please note, it is the total number of valence electrons in free atom minus the total number of non-bonding, that is lone pair electrons, minus half of the total number of bonding, that is shared electrons. We'll understand it more clearly by an example. This counting is based on the assumption that atom in molecule owns one electron of each shared pair and both the electrons of a lone pair. Let us consider the ozone molecule O3, and its figure is, its Lewis dot structure is shown on the left hand side. The Lewis structure of O3 may be drawn as shown in the figure, and the number of atoms have been numbered as 1, 2, 3. So this is one atom number 1, atom number 2 and atom number 3. The central O atom, that is number 1, equals 6 minus 2 minus half of 6. That is 6 is the total number of valence electrons for electron 1, atom 1. The total number of valence electrons is 6 minus the total number of non-bonding atoms, that is lone pair is 2 here in the case of atom 1, minus half of 6 minus half of total number of shared electrons, that is 6. That equals to, simplifying, becomes 1. Similarly, for atom number 2, it is the formal charge, the total valence electrons in the free atom is 6 minus the number of lone pair electrons in atom number 2 is 4 minus half of number of bonding, that is shared electrons, is half of 2, that is equal to 0, simplifying. Similarly, finally, for atom number 3, the total number of valence electrons are 6 minus total number of lone pair bonding electrons are 6 minus half of 2, that is the number of shared electrons 2, that becomes minus 1. Hence, the structure, the Lewis dot structure along with its formal charge are shown here on the right hand side. Here the formal charge is written on the top of this O atom number 1, that is, here we should write plus, and on this atom, that is atom number 3, you have to write minus. Thus, formal charges help us in selection of lowest energy structure from a number of possible Lewis structures for a given species. Generally, the lowest energy structure is the one with the smallest formal charges on the atom. The formal charge is a factor based on a pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. Next we'll discuss about the limitations of octet rule. The octet rule, though useful, is not universal. It is quite useful for understanding the structures of most of the organic compounds, and it applies mainly to the second period elements of the periodic table. There are three types of exceptions to the octet rule. First exception is the incomplete octet of central atom. In some compounds, the number of electrons surrounding the central atom is less than 8. This is especially the case with elements having less than 4 valence electrons. These examples are LiCl, BeH2 and BCl3. One case is shown of BeH2 is shown on the right hand side of the screen. This is the one exception, that is BeH2. Li, Be and B have 1, 2 and 3 valence electrons only. Some other such compounds are AlCl3 and BF3. The second exception is the odd electron molecules. In molecules with an odd number of electrons like nitric acid NO and nitrogen dioxide NO2, the octet rule is not satisfied for all atoms. Example is shown on the right hand side here. So the octet rule is not followed here. The third exception is the expanded octet. Elements in and beyond the third period of periodic table have, apart from 3s and 3 orbitals, 3d orbitals also are available for bonding. In a number of compounds of these elements, there are more than 8 valence electrons around the central atom. This is termed as expanded octet. Obviously, the octet rule does not apply in such cases. Some of the examples of such compounds are PF5, SF6, H2SO4 and a number of coordination compounds. Interestingly, sulfur also forms many compounds in which the octet rule is obeyed. In sulfur dichloride, the S atom has an octet of electrons around it. Please see the diagram on the right hand side in respect of PF5, where 10 electrons around the P atom, and SF6, 12 electrons around the S atom and 12 electrons around the S atom. Please pause the video and note down these Lewis dot structure figures. Other drawbacks of octet theory are some noble gases, for example xenon and krypton, also combine with oxygen and fluorine to form a number of compounds like XeF2, KrF2, XeOF2, etc. This theory does not account for the shape of the molecules. It does not explain the relative stability of molecules being totally silent about the energy of the molecule. Ionic or electrovalent bond. From KÖssel's and Lewis treatment of formation of an ionic bond, it follows that formation of ionic compounds would primarily depend upon the ease of formation of positive and negative ions from the respective neutral atoms. The arrangement of positive and negative ions in the solid, that is, the lattice of crystalline compound. The formation of a positive ion involves ionization, that is, removal of electrons from the neutral atom, and that of negative ion involves the addition of electrons to the neutral atom. Thus, an ionic bond is the electrostatic force of attraction between cation and anion formed by complete transfer of electron from one atom to another so as to attain the nearest noble gas configuration. Please note, the ionic bond is the electrostatic force of attraction between cations and anions formed by complete transfer of electron from one atom to another so as to attain the nearest noble gas configuration. Ionic bonds will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative values of electron gain enthalpy. That is, for easy formation of ionic bonds, there should be comparatively low ionization enthalpies and high negative values of electron gain enthalpy. A qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the electronic species in gaseous state. So, the qualitative measure of stability of ionic compound is thus provided by its enthalpy of lattice formation also. Ionic compounds in the crystalline state consist of orderly three-dimensional arrangements of cations and anions held together by Coulombic interaction energies. These compounds crystallize in different crystal structures determined by the size of ions, their packing arrangements, and other factors. The crystal structure of sodium chloride, that is rock salt, for example, is shown on the screen. Lattice enthalpy. The lattice enthalpy of ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent electrons. So, the lattice enthalpy is the energy required to completely separate 1 mole of solid ionic compound into gaseous constituent electrons. Factors affecting lattice enthalpy. First is the lattice enthalpy is the factor that affects the lattice enthalpy is charge on the ions. The charge on ions is directly proportional to force of attraction between ions, which is directly proportional to the lattice enthalpy. Please note down all these important points. Thus, the lattice enthalpy of bivalent ions is greater than uni-bi or bi-uni ions, which is greater than univalent ions. The second factor which affects The lattice enthalpy is the size of ions. So, lattice enthalpy is directly proportional to the force of attraction between ions, which in turn is inversely proportional to size of ions. That is, lattice enthalpy is proportional to 1 over the size of ions. Now we will further take up multiple choice questions. Question number 1. The electronic configuration of 4 atoms are given in brackets. That is, element P 1s2, 2s2 and 2p1. And for element Q it is 1s2, 2s2 and 2p5. And for element R it is 1s2, 2s2, 2p6 and 3s1. And finally for element S it is 1s2, 2s2 and 2p2. The element that would most readily form a diatomic molecule is, that is, amongst the 4 elements given above, the element we have to identify the element which will most readily form a diatomic structure. 4 options are given as answers. Option A P, option B Q, option C R and option D S. So we have to identify the element amongst P, Q, R and S that would most readily form a diatomic molecule. Please mark your choice and I will give the explanation. By sharing 1 electron each, both the atoms of Q will get a completed octet. So here this is Q is the answer that is given in option B. Here you mark your choice answer. Next question. 2 elements P and Q combine to form a compound. If P has 2 and Q has 6 electrons in their outermost shell, what will be the formula of the combined compound? Option A PQ, option B P2Q, option C P2Q3 and option D PQ2. So you are required to identify the correct formula of P and Q. So let me give the explanation. Valence electrons of P is given as 2 and Q is 6. So therefore P minus 2e to the power minus 2 gives P2 plus. Similarly, Q accepts 2 electrons Q plus 2e minus to form Q2 minus. Since both show a valency O2, the formula for compound will be PQ. So this is given as option A. Please mark it. So option A is the correct answer. Next question. How many number of electrons are involved in the formation of nitrogen molecule? Please read the question once again and see the options. Option A 3, option B 4, option C 8 and option D 6. So we have to identify the correct answer, that is we have to select the number of electrons which are involved in the formation of a nitrogen molecule. Please see the diagram on the screen. For 2 atoms of nitrogen, the Lewis dot structure formula is shown here, and in between the 2 nitrogen atoms there are 6 electrons, that is triple bond here, 6 electrons. So 6 is the correct answer. So mark the option D as the correct answer. Next question. A pair of electrons is present between 2 identical nonmetals. Then the electrons is shifted. We have to answer 4 options are given. Option A is that is shifted to one of the atoms. B is shared equally between them. Option C is undergoes addition reactions, and option D is have the same spin. You have to identify the correct answer and remember and identify. And the correct answer is option B. That is, a pair of electrons is present when between the two non-metal is shared equally between them. Next question. In which of the following molecules octet rule is not followed? Four options are option A NH3, option B CH4, option C CO2 and D NO. In molecules with an odd number of electrons like nitric oxide NO and nitrogen dioxide NO2, the octet rule is not satisfied for all atoms. In the given options, option D is the correct answer. Please mark it. Next question. In a covalent bond formation, the transfer of electrons takes place. Option B, equal sharing of electrons between two atoms takes place. Option C, in covalent bond formation, electrons are shared by one atom only. And option D is, in a covalent bond formation, electrons are donated by one atom and shared by both atoms. Please remember, and the correct answer is B, option B. Please mark it. Next question. Two elements X and Y combine to form a compound XY. Under what condition the bond formed between them will be ionic? So this ionic bonding will be continued in the next video, and please remember that if the difference for the formation of ionic bond, the electronegativities of two atoms should differ by more than 1.9. Hence option B is the correct answer and mark it. Next question. In which of the following species the bond is non-directional? This also we are going to cover in our subsequent videos. Please, the four options are given. Option A NCl3, option B RbCl, option C BeCl2 and option D BCl3. Please note that RbCl is an electrovalent compound, hence bond involved is non-directional. Hence option B is the correct answer. You please mark it. Next question. Which of the following shows the Lewis dot formula of CO2? So here four options are given. A and B, C and D, and the Lewis dot structure or formula is shown in the here in the second column. You have to identify the correct Lewis dot formula in respect of compound carbon dioxide. So you have to remember the Lewis dot formula structure for carbon dioxide and mark it the correct one. The correct one is option A. Next question. Which of the following molecules contains covalent and coordinate bonds? Four options are given. We have to identify which compound or molecule has both covalent and coordinate bonds. Option A CCl4, option B H2SO4, option C NaCl and option D MgOH2. So for analyzing, please see the insert box and the correct answer is H2SO4, and therefore there is a single bond as well as the double bond. So the correct answer is H2SO4, which is given as option B. Please mark it. Next question. Sodium chloride has crystalline structure made up of Na plus and Cl minus ions. Why does NaCl not conduct electricity? Four reasons are given. A. The ions of NaCl become mobile only in molten state and are not free to move in solid state. That is option A. Option B is the crystalline structure does not have ions. Option C is when bond is formed between ions, they lose their charges. And option D is none of these reasons given above that. So you have to give the explanation. Due to electric force of attraction, the ions do not move when electric current is applied in solid state. The ions become mobile when melted or dissolved in a polar solvent and conduct electricity. Hence, mark the option A as the correct option. Next question. Which of the following elements forms predominantly covalent compound as compared to the other elements which form ionic compounds? So you have to identify the element which forms covalent compound as compared to the other elements which form the ionic compound. So predominantly covalent component should be marked. Four options are given. Option A beryllium, option B Mg, option C Ca, and option D Sr. Smaller size of cations and more predominantly covalent compounds are formed. So smaller size of cations is present in beryllium Be. So option A is the correct choice and you mark it. With this, we come to the end of lecture 1 of chemical bonding and molecular structure. In the next lecture, that is lecture number 2 of unit 4, we will discuss ionic or electrovalent bond, lattice enthalpy, bond parameters, and if time permits, we will also discuss about VSEPR and valence bond theory. Till then, goodbye.